Дорогие друзья, надеюсь, все в порядке. Dear friends, today we have a lecture exploring ice in the solar system by Anton Ivanov, PhD professor and director of Space Center Skolkovo Institute of Science and Technologies. Anton, are you here?
Yeah, I was unmuting myself. Yes, I'm here.
Okay, Anton, please.
All right, so welcome everyone. Today I'll make a brief lecture about ICES in the solar system. Let's see. Let me start my presentation. All right.
Okay, it's okay.
Okay, so welcome everyone to the program. Well, Torivan, thank you very much for inviting me. I've been affiliated with this program for a very long time, let's put it this way, since 2007, so it makes it almost 15 years, Torivan.
What? And
Not yet.
yeah, 15 years with you, with your
Yes.
university. Yeah.
So I'm very happy that it's going on despite all of the coronavirus and other things. So I'm very happy to present it. I'll try to make it relatively brief. I know that you have a project regarding Enceladus, so I will try to address Enceladus as well. And then we'll see if you have any questions, but I'll be happy to answer them. So anyway, let's start. All right. So what I wanted to start at the very beginning. It's like where the water in the solar system is coming from, and obviously, since it's cold in most places, it turns into ice. Actually, water as a product of hydrogen and oxygen was produced very early after the creation of the solar system. And I picked up one of the YouTube videos on the creation of the solar system, which was created from a molecular cloud, and then it started to rotate to form a protoplanetary disk. And actually, water was equally distributed everywhere in this protoplanetary disk. So to paraphrase a famous saying, water was everywhere. And then the solar system started to, let's say, to form. First, these little planetesimals have formed, so something what you see on the screen. So this kind of very small fragments that started to stick to each other electrostatically, and then with time they grew to larger objects that we know now, and they formed planets and asteroids, and then things started to collide. But again, the water was more or less distributed everywhere. So that's my main takeaway message. At the beginning of the solar system, water was everywhere, but then it started to be distributed because some planets were hot, some planets were cold, and so on and so forth. So let's see, what do we have now? Let's see. Okay. So I decided to start with places where you least expect ICES to have in the first place. And actually, you do have ice on Mercury, although your first, reaction is that Mercury is the closest planet to the sun, but no, it has ice. And actually, it came as a very large surprise to everybody who was involved in this first experiment. So what people have done is they basically they shined radar onto Mercury North Pole because there was such an opportunity from Earth. And to their surprise, the signals came very strong from the North Pole, and the only explanation was it was ice hidden in craters. And later on, these observations were confirmed by the MESSENGER mission with the use of mercury laser altimeter. So what happens there? Let's see if I can. I wanted to draw something here, but let's see. I'm not sure if I actually can. Let me see something real quick. Yeah, I'm still sharing and see, annotate, and draw. Okay. So what happens on Mercury in here? See, I don't want to. I'm going to talk about ice on Mars in my next lecture. Unfortunately, I don't have my iPad where I typically do this kind of things. But anyway, so what happens with Mercury? So here you have the sun. Kind of like this. Yeah, let's make it yellow. Okay, so this is the sun. And here, let's say we have Mercury, which is, of course, very hot. So this side here that faces the sun is extremely hot. However, there is no air, so there's no convection. And once the Mercury turns around, the other side actually becomes very cold. So this side of Mercury is extremely cold because there is nothing shining in it. There is no atmosphere. There is no water to carry the balance. And here, see, at the North Pole, you have these craters, which kind of like this. And if you trace a ray from the sun, it hits right over the rim. So, and since the rotation of Mercury is, it's slightly inclined and goes in this direction, sun actually never penetrates to the crater. So what happens if you look from the standpoint of one of these craters in here? So here's the crater, kind of like this, and sun never shines into certain directions, and ice can very simply survive in here. Is okay, I don't know if you can ask questions in the meantime, but the mechanism is actually quite simple. Since you never have sun, so this is called permanently shadowed regions, and sun never shines into these areas. Now, what's interesting is that exactly the same mechanism works on the moon. So we have discovered there is some kind of snow, or I mean some kind of ice in the permanently shadowed regions in the moon. So this is why you can hear now a lot of space agencies, they're talking about that they can go to the moon and harvest water, but it's actually, it's a little bit more difficult than this. Let me explain you why. On the moon, so let's see, here is our shadowed crater, and goes like this. And the way ice is formed inside on the moon is that molecules, water molecules, they kind of hope inside the crater like this, together with various pieces of dust and some other things that are there. And there is a little bit of ice in here, there. And in the end, the mixture that you get, it does contain ice, but it's also mixed with all kinds of what we would call dirt, okay? What we would call dirt on the, here on Earth. And actually what you're seeing on the moon is not a straightforward ice, but it's some fancy mixture of dust and particles and pieces of asteroids and Some of that is, let's say, icy. So it's very, very difficult to extract in terms of, like, if you can't just come and drill, like what you would do in some other areas. Did you see my drawings, Виктория Ивановна? Видно было, что я рисовал?
Yes, yes, yes,
Ah,
yes,
okay.
yes. It's good.
Right, right.
I understand good.
So it's okay. So I mean, it's not very convenient to draw on the screen like this, but anyway. So in principle, for both, let me just quit this. For both Mercury and the Moon, there are lots of papers that have been written on this. And I don't want to dwell on this for a long time because I know that you're mostly interested in Enceladus. But I just wanted to tell you that, okay, guys, ice exists almost everywhere it can exist, except for places that are actually heated directly by the sun, like Venus. And it's in general very hot in Venus. So I guess Venus is probably the only planet in the solar system that doesn't have any ice, at least that we know of. Maybe it's somewhere very deep under the ground. Now let's talk about my favorite planet, which is Mars. We have a lot of water on Mars. So on Mars, the situation looks like this. These two maps are topographic representation of data that was obtained by Mars Orbiting Laser Altimeter. This is an instrument that was flying more than 20 years ago. And it was the first instrument that collected precise topographic maps of Mars. Before this, we had no idea that it existed. And we actually knew from some spacecraft in the 70s that there are polar caps on Mars, polar caps in terms of glaciers. But nobody knew how deep they were. And actually, Mars Orbital Laser Altimeter was the first mission that actually discovered the thickness of these ice caps. So here on the left, you can see the North Pole, and on the right, there is a South Pole cap. Both of them are roughly in size the same as Greenland. If you know what, you can Google the size of Greenland. So this is roughly the size of the ice caps. Also, Greenland is approximately 2.5 kilometers thick, and Martian ice caps are also, both of them are about 3 kilometers thick at the center. So you can also see the troughs, which are the sign of erosion that happens all the time. Now, it's important to understand that this is probably 99% of all the ice that we have discovered on Mars in the last 20 years. And we looked very intensively. We looked with two kinds of radars. We looked with a lot of cameras. We looked with Mars rovers. And for the moment, these two features, these two ice caps, is most of the ice that we have on Mars. We have a couple of other candidates on Mars closer to the equator, where we think water is possible, but it's still, let's say, under investigation, and we don't have enough time. Now, how the water got there? Probably, again, Mars, as all other planets, had water. In fact, we have a lot of evidence that there were lakes on Mars, that there were rivers on Mars, that there were bodies of standing water on Mars, that there were some signs of what's called catastrophic outflows that actually formed some of the channels on Mars. But then all of the water just evaporated with time. It's because Mars doesn't have any magnetic field. So anyway, there is some, because the solar rays break up H and O, and basically all oxygen falls out on Mars and oxidizes everything. This is why Mars is red, and hydrogen just evaporates in the atmosphere. So you have to be super grateful that Earth has a strong magnetic field. If we hadn't had magnetic field on Earth, there would be no life, because all of the water would be destroyed by the same process that's being destroyed right now on Mars, because Mars doesn't have any magnetic field. We wouldn't be protected against solar wind particles, and all life would have been killed on Earth. So magnetic fields save us a great deal. So that's water on Mars. Actually, this is another view of Mars, and the caps that we have just looked at are actually pictured on the top and on the bottom. And this is another instrument. This is called neutron spectrometer. It was flown in the missions that followed Mars Global Surveyors and MOLA, and it basically looked at how many neutrons you have reflected from the ground due to various geothermal processes, and it was basically a reflection of a number of solar wind particles and so on and so forth. Now, the thing is that this neutron spectrometer, it was very sensitive towards certain fluxes in certain energy ranges. And what we have seen that once the spectrometer flew over, let's say, polar regions, they could see a rapid decrease in fluxes. So which means that these regions contained a lot of water in the subsurface, because water effectively stops some energetic neutrons to flying towards the detector. So it was a deficiency. And this deficiency is mapped into this south polar region below 60, where there's probably quite a bit of ice under the ground. And there are a couple of other interesting regions which might have some bound water, but it's strongly bound inside the mineral, so you can't really say, I mean, you can't really extract it. No, it's not something where it's not a place where you can actually land and dig out water. But that being said, there was a mission that's called Phoenix. It flew in 2007, I think. And they landed in the polar region at 72 degrees north. And what they did, they dug a little bit under the ground. So on the picture in the right upper corner, you can see again our North Polar ice cap that we have already seen, and the blue dot denotes where the mission have landed. So it's kind of far away from the pole, but still in the region that was marked up on this blue and red map is one of the regions that might have some water. So anyways, they dug up a trench, they looked at this white stuff, and some of the white stuff had evaporated in 3 days, which told to the scientists, okay, if you have white stuff that's there one day and then it evaporates after several days, most probably it's ice. I mean, it cannot be sugar, or it cannot be something, or it cannot be salts, because salts don't evaporate. So most likely this stuff is ice that evaporates. So it's kind of confirmed the observations that were done by this neutron spectrometer that was done by Boynton and Paul. So anyway, just some signs of the water on Mars. So this is current ice. I mean, we're not talking the ancient waters. This is a whole other lecture, but this is what's currently available on Mars. I mean, there is still a lot of discussions about how much ice that actually is, but we don't have any other data, so there is not much to discuss, at least at the moment. So that's your water on Mars. You're supposed to laugh here. Okay, this is an animation. I'm not sure if it's going to work. Let's see. Is it? Okay. So this is an animation of an Italian radar. It's called Charad. I'm pretty sure the quality is kind of bad, but it shows a principle of how data are collected from underground. And what we have done, we have flown two radars, Marsis and Charad, to look under the surface of the ice caps. And this is what the cap looks like underneath, and we'll talk about this in just a second. Kind of has to do something with the formation of the caps. And so actually what you can see here on this particular picture is that, well, there is obviously the basal layer, but then let me do a little bit of drawing. Oops. I can't. I have to run the movie to the end. It's a beautiful simulation, so let's wait for it. So this is a radar. It flies over Mars, looking into the ice caps. And I'll just do a little bit of annotation on my own. Yeah, you can see the internal structure of the ice caps, and we know exactly how deep they are and what the internal structure is, so we know a lot of information now. And here you can see that there is, on this picture, there is this famous basal layer like this. And actually, we don't know what it is. So, I mean, it's clearly something which is different from your regular ground or basalt. And it's some sort of very old ice. And actually, there is still a huge debate in the scientific community what exactly that is, but it's probably some sort of dirty ice. And on top of this sits this big structure, which is basically a layered cake of what we call layered deposits. And while it's layered deposit, I'll show you in my next slide. So I'll just stop this. I will erase everything. And I will continue with the presentation. Fixing this. So this is the picture that is obtained, that's called a radiogram, which shows a very high detail of the 3D structure of an ice cap. So what you can see here is these layers. And layers have been formed in a very long time due to very strong changes in the Martian climate. And here, what it's talking about is basically the Mars wobbles quite a bit, and it's very, its insolation changes. So the amount of sun illumination that it receives changes drastically year to year. And actually right now it's in some very specific conditions. In the last, let's say, 100,000 of years, it didn't change much. And what you see are basically layers of dust intermixed with layers of ice that was depositing on the ground. So what this picture is saying is that the ice cap structure is probably best correlates with an age of about 4 million years. So in fact, if you think about, the age of a planet, which is 4 billion years, and we have these eons in the history of the planet, so roughly each eon is 1 billion years old. And the latest epoch in Martian history is called Amazonian, which is approximately 100 million years old. This is sort of how time works, in geologic time works on Mars. And these caps are only 4 million old. So what you can say is that the caps are actually very young features on the surface of Mars that were formed relatively recently in Martian history. And what happened before them, we actually don't know. So it's still a little bit of mystery. But anyway, there was a science paper in which Isaac Smith and his colleagues have published a paper about 5 years ago, 6 years ago. Quite interesting read based on Charad data. It's the Italian writer. It's actually quite good paper. All right, let's go next. Okay. Now we're going to Saturn, and it's a little bit closer to what you guys were studying recently. So there is an important mechanism that's called tidal heating, and it's important for Enceladus. And in fact, it's important for two bodies in the solar system. It's important for Enceladus and for Io. So what happens is that when a satellite, let me try to illustrate this again. Let me see if I can do this. Oops. Let's go back to Enceladus here. I'm going to give myself a new slide because I just wanted to explain it a little better. So let's see, annotate, draw. So let's imagine that you have some very large planet. And then right next to it, you have a smaller planet. Like this. So what happens is that the force that's acting, the gravity force that's acting on this part is small, is larger than the force that's acting on this part. So let's say this is gravity force F1, which acts here, and this is F2 that acts on a parcel that's here. And this is effectively how it's attracted to Jupiter or Saturn. So this has to be Jupiter or Saturn, and this is Io or Enceladus. So and F1 is more than F2 just because it's closer. And effectively, if you calculate F1 minus F2, then the resulting force will actually be acting, let's say, basically this way, consistent with F1. So, but if you have actually this body is actually rotating, which means like this, then what happens, let me just draw it again here. Depending on the rotation period, this body is pulled apart like this, and then it's actually forces doing like this. So it's effectively, as Io is rotating around Jupiter, it kind of goes like this. And when you're doing to a very large body with an internal force, it creates a lot of temperature inside. And temperature inside is, of course, rising, and all kinds of gas starts to expand. So this is why you see these geysers on Io, and this is why you see geysers on Enceladus. So this is kind of important. These are two very specific bodies that are affected by this tidal heating effect, which is effectively, if you have a small body close to a larger body, then it's basically heated from the inside due to these friction forces. So this is what's important to understand about Enceladus. So, see, I want to stop this. Yeah, just going back. Oops. Wait. You just need to erase everything. And yeah, go back here. So anyway, so IO is one of the places that's affected by this, and we knew about IO for a very long time. I mean, basically, it was discovered. The geysers on IO were discovered by Voyager in 1970s. But Enceladus was relatively new because, in fact, no spacecraft was flying very close to Enceladus. And these tidal jets were discovered during a flyby on November 30th, 2011. So that's relatively fresh discovery. After this, Cassini flew by Enceladus a few more times, and they confirmed these jets, and they did all kinds of mass spectrometry on it. Turned out to be some sort of water and methane mixture, which led to obviously theories that there is actually an ocean underneath the Enceladus. Let's see. Well, another place which is very icy is Europa. It's a satellite of Jupiter. It's a little bit farther away than Io, so it does not suffer too much from external heating. But what we know is that it's covered by these crevasses, which are created by movement of ice underneath the ice core. And people have explained it is that basically, due to internal processes, due to heating of the stuff that's underneath this ice crust, you form these crevasses, and they sometimes let the water out, or whatever it is underneath. And it's a very complex geologic process. And in fact, we have not investigated Europa in great detail. So we don't know what's going on underneath. It's very difficult to explore Europa because of radiation belt of Jupiter. And we don't really know what's going on. It would be very interesting to send a mission there. And I think there are a couple of efforts are underway, yes, as we speak, of course, by NASA. Okay. So this is a close-up of one of these crevasses on Europa. I think they are just beautiful, just in terms of naturally created image. And I think what happens on Europa is that these crevasses, they open up a little bit, and as soon as they open up, they are filled with liquid, which freezes immediately because it's just so cold, and there is not enough internal heating to actually create a geyser or something. But there's definitely something going on Europa, and we don't know much about this something. So let's see. Right, so this is an explanation of tidal heating. So as you fly around Jupiter, your planets kind of go like, the satellites go like this and create internal heating, which in turn heats up whatever water is inside, creating the jets. And these are a couple of interpretations of what might be happening on Europa. So one explanation, if you have these geysers underneath that actually heat up, and there is an ocean underneath Europa. Another explanation is that there is not enough heat, so there is water, and then there is kind of icy water. So there is like water very heavily mixed with ice, and it creates some of the plumes. So yeah, we don't know what's going on because we haven't flown anything around Europa for a while. Let's see what else is there. Right. So, and this is a close-up of jets of Enceladus. So there's one. Here is another one, which is colored. Actually, this is a composite picture of two instruments. There's one that was actually imaging water particles, which you see in blue, and the imaging spectrometer actually image the Enceladus, and then they convert these two pictures together to give this beautiful view of Enceladus. And here is one of the explanations of what's going on in Enceladus. So the idea is that it's an icy satellite, so which means it's covered by ice. But there is actually the body of water that's inside Enceladus is not all that big. It's actually kind of small. And it's all concentrated down near the South Pole. So all we see is this icy satellite. It's going through this tidal heating, but it's much smaller than, well, it's actually comparable to what we have on Io. But it's not all ice under the surface. There is actually a very solid rock core inside, but it's a very small, let's say it's not a lake, it's like a sea of water. It's not an ocean, it's a sea of water in the South Pole, which is created by melting, due to tidal heating. And these are the geysers that we see. So that's one of the explanations of what's going on Enceladus. And there is actually a little bit more that people have tried to explain about Enceladus. So basically, there was some, in addition to water ice, there was some methane that was observed in these jets. So Cassini did a really good job. And one of the ideas was that methane is created by mixing a material that's called olivine with water. And olivine is basically a rocky core, and it's near the hydrothermal vent, which is effectively created by tidal heating. Water ice is trapping molecules of methane, and then they actually evaporate together with the rest of the water. Well, what we don't know about it, we don't know how much water there is on Enceladus. We don't know precise mechanisms of these jets. Also, we don't know how much water there is on Europa. And the key question of all, can this environment support life? Like, there is enough heat, there is enough water, there is some methane, so maybe you can have some methane-eating bacteria, which we've never heard of before. Maybe there is some ice, there is some life underneath the surface of Enceladus and Europa, so we just don't know about it. So that would be definitely very important discovery of this century if somebody can find signs of life on Enceladus. That's actually all I wanted to say. This is a beautiful picture of Saturn taken by Cassini. And that's all I wanted to say. Maybe you have some questions. Victoria Ivanovna, я все.
Dear friends, do you have questions? Please.
Yeah, I have a question. So maybe I didn't hear, but one more time, how the water, how people understood that we have water on different planets, so the mechanism.
Well, water was distributed evenly between all the planets. So when the planets were created, everybody had the same amount of water. But each planet has its history of what's happened with the water. So on Mercury, it's just evaporated because it's very hot. There is some water that's left in the permanently shadowed regions up in the north, but this is all there is to it. On Venus, it was a similar effect. I mean, on Venus, it's even more complicated because there was some water on Venus in the beginning, but then due to lack of the magnetic field on Venus, all of the water has evaporated, and that led to changes in the core. It led to absence of plate tectonics, and it led to huge volcanic eruptions, and there was a greenhouse effect. Anyway, Venus have warmed up, and all of the water has evaporated as well. On Earth, well, we have plenty of water. We are the only planet that's likely to have it because we are protected by a magnetic field, and Earth does not escape the planet. On Mars, there is still a little bit water left, but just mostly because it's so cold. And there's actually plenty of water on Jupiter, on Saturn, and on the icy satellites. So what I'm saying is that water was available to everybody and every planetary body in the solar system. There is some still that's transferred by comets and asteroids, but there is a little bit of debate of which body has more ice inside, comets or asteroids, because apparently, based on what we have seen in Rosetta, comets are not that rich in water compared to asteroids. So there.
More questions? Please.
I have a question. You paint a picture with a tidal force caused by gravity of satellites, and does the gravity of the planet, which caused would oscillate of satellite, affect the location of water on a satellite?
It doesn't, because tidal heating is it's basically applicable to everywhere. So let me do a quick draw again. Just a second. I'll sharing. So basically, if you look at the tidal heating from the point of view of a planet, so let's say this is Io. Then basically tidal heating heats up the planet from the inside. So it's basically heating it from the inside, and since the planet rotating, it basically the heat is the same everywhere. Now, the thing is that, actually, I think what you're asking is why is it different on Enceladus? I don't know. So what we see on Enceladus is that on the South Pole, what we see on Enceladus is that there is actually some water melted on the South Pole, and let's see, the thing is that the planet is actually surrounded by ice, so ice is everywhere. And but we only see jets near the South Pole. So the question is, why the heat, which is kind of generated in here, only goes to the South Pole? I don't know. It's a good question.
Okay.
So I have to say that I haven't read about, from just general things. I mean, you'd think that you have jets in other places, like here, and maybe there, and maybe there, but we don't see them. So it's a very good question to ask why we only see jets in the South Pole, because if you have heat that's equally distributed inside the planet, then it should go out everywhere, and we should see jets everywhere, but we only see them in the South Pole. So I don't know.
It's related
Something to think about.
Of Saturn, maybe.
Well, you have, yes, I mean, you have to look into details of how, let me, unfortunately, this is not my field exactly, like looking at icy satellites. I know much more about Mars, but so let's say here is Jupiter, Saturn, and here is Enceladus, and maybe there is something that deals with rotation of the satellite. For example, if it's rotated around this axis, or if it inclined more this way, or inclined a bit more this way. So you have to look into some of the things in orbital dynamics and a few other things. Maybe there's some internal things on Enceladus which favor South Pole, but again, it's not something that I can answer right away, and I'm pretty sure a lot of people have thought about it, and you can look for papers about it where people will discuss why they think Enceladus has southern jets, but not jets anywhere else. But it's a good question. It's something to think about.
Okay, thank you.
Guys, please, questions.
Can I ask you some questions? First of all, thank you very much for their interesting lecture, Professor Arnold. And I would like to ask you, so if somebody just theoretically would like to reach the subsurface ocean of Enceladus, what, in your opinion, could be the way to do it? Just theoretically.
Well, it's difficult. I mean, the thickness of the ice caps is very, very big, and you have to drill through quite a lot of ice. I think the deepest wells on Earth are something like 1 kilometer, and there you have to drill through like 3 kilometers, and you have to do everything automatically. I mean, in Antarctica, you have crews of people who help change the drills and other things. And to do it fully automatically in conditions which are much, much, much worse than here on Earth. Because on Earth, okay, in Antarctica, you benefit from the daylight, and the temperatures are actually not that cold, so stuff is not freezing so intensively. So it's a difficult problem. I mean, I don't know. We thought about this when we were thinking about drilling down with a jet of hot water going down the north cap of Mars, but you have to protect the hole that you're drilling such that it doesn't freeze. And that's you basically have to leave some sort of tube behind you such it doesn't freeze, and it's difficult.
Maybe if we use some technology like heating of ice, so just melting our way through it, maybe you could
it will be very difficult. It will be very difficult to heat 3 kilometers of pipes. Yes.
Okay.
So I mean, just the amount of energy you have to spend, which be dramatic.
Thank you.
Thank you. Yeah, do we have questions, please, Mr. Kumar?
You have to unmute.
Yeah, thank you, Professor, for your lecture. It's really appreciated. I'm Pratik from Cardiff University in the UK. I was just wondering, the instrument you talked about is Sharad instrument, I guess, on board of Mars Reconnaissance Orbiter. So that has the frequency from 15 to like 25 megahertz active instrument, and which basically fires the signal to the Martian surface and reflects back, and you get the signal on the Sharad antenna. So I was just wondering, of course, the strong radar signal that's coming on the Sharad antenna could come from ice, a rock, or different geological surfaces. So in terms of the antenna size, so I'm trying to pose a question in terms of space instrumentation, that what could be the optimal size of the Sharad antenna in order to distinguish the spectral signature of, the water that could be present on Mars and the geological features present on the Mars. So I'm trying to guess, get an idea that how do you distinguish the electrical reflection characteristics of rock, sand, or
Okay.
yeah.
Right. Well, the size of the antenna I don't remember, but I mean I think it's consistent with the wavelength, so it's not very big. I think it's a meter or two or something like this. I don't remember the exact size, but you can just find some charade description document in paper, and it will tell you what the antenna is. Now the thing is that what charade is sensitive to, and Mars is for that matter, is the difference in the interface electromagnetic properties. So basically, if you have two materials with significantly different conductivities, then you get a reflection of this interface. And this is what you see in charade. This is what in charade, what you see, you don't see water, you don't see, I don't know, hydrogen or basil. I mean, what you see is difference in interface reflections. Unfortunately, actually, we were quite surprised to see that the signal in charade and Mars penetrates very, very deep, all the way to the basal layer on Mars, which means that there are not very many interfaces, so they don't consume all of the signals. And the ice is relatively clean. If there was a lot of dust, it would just eat all of the signal would scatter. And the structure of ice caps on Mars is such that it's not scattering the signal too much. So it's actually mostly ice, and you can see very large reflections, very intense reflections that are coming back.
And I was just wondering, in case of charade, do the Italian Space Agency, or I don't know, I mean, like they are the manufacturers, but does they use the compressed sensing algorithm for data transmission? Because this question is important in terms of data allocation budget, because the huge amount of data needs to be transmitted, and that should come within the MRO data budget as well. So I was just wondering about the algorithm they use in some
the answer is it's called onboard SAR processing. So it's a very specific processing. It's a synthetic aperture radar, and all of the processing is done on board for exactly this reason, to not to send down the data, the original data. Of course, there is a capability to send raw data just to make sure that onboard processing works right.
But one could argue that the onboard spacecraft processing should be nominal as possible, should be a minimum as possible. Of course, I mean, people trying to implement AI ML on spacecraft onboard processing, but at the same time, in terms of space instrumentation or data, the various constraints on the spacecraft, one could argue that you have to minimize the processing budget on the spacecraft. What do you think about that?
Well, it's a trade. I mean, you have to trade off the quality of the data. And actually, the problem is that radar data compresses very poorly, because it's so noisy, and if you just run something like JPEG or PNG algorithms, I mean, it will compress very poorly. So you actually have to do things like Fourier analysis and some simple sums and so on, right there on board. You mentioned compressive sensing. It's actually quite intense on board, and it's after compressive sensing, it's mostly applied for hyperspectral imagery on Earth, but for the radar, I don't think anybody has discussed it yet. And it's quite intense in terms of processing power, and you have to remember that there are very significant restrictions on the power. And actually, the hardware that's flying in Shara was made in the year 2000. It was made more than 20 years ago.
Yeah.
So, and it also on top of this, it has to be space qualified, which means that we're basically flying technology from 1995, which is extremely not powerful. So all of the traits have to be taken into account. Right, but right now, yes, I mean, there are PGAs that allow you to run some ML stuff, and this is sort of the cutting edge. And but before we send it to Mars, we have to verify that they work fine here on Earth, and then in 5-6 years we can send it to Mars. Yes, so it's coming.
Yes, and I also have some question for my colleague. We are asking because this is our basically technical task to get to the subsurface ocean of Enceladus. So you think it would be more preferable to drill, so without not consider heating at all? No.
I don't know. It's something I haven't thought about, and it has to come out in your study, and you have to consider all of the options and see what works. It's not something that you can answer like this.
And another question, do you think we somehow could use geysers which are basically already connected to the subsurface ocean, or it would be just too dangerous and infeasible technically?
Yeah.
So what was the question?
About geysers, could we use geysers which are not active
Okay.
the ocean?
We don't know much about geysers, but I mean, it would be. I mean, if you go into, for example, Yellowstone, then you can see that these geysers are pretty regular in terms of how often they erupt, and that probably gives you a window of opportunity to go through the vent and see what's inside. So you basically don't have to drill anything. It's just an underwater probe, but it can be kicked out once your geyser is active. And my impression is that geysers on Enceladus are active pretty much all the time, at least what we see. And probably the vents that are not active may be frozen over. So anyway, we don't know much. I mean, you have to fly a reconnaissance mission first before you can decide what to do.
Okay, thank you very much for your answers.
Guys, questions, please. No more questions? Okay. Thank you so much, Professor Ivanov. Anton, thank you.
You're welcome.
We invite you to our final presentation. If you will have a possibility, please, it will.
Thank you very much.
It will be next week on Thursday. Okay, we will send you our link. Thank you so much.
Very much.
Yes, we have a break, and we will have another lecture by Mr. Abby at 6:30. Please, at 6:30.